Thanks for the intro. Yes, I'm Paul Yang, and today I'll be talking about scaling and syncing warehouses on AWS. This talk will probably be most useful to you if your warehouse is also on AWS, or you're planning to scale from the terabyte order to the petabyte order. In this talk, I'll go over some of the cluster architecture decisions that we made, along with the systems that we built to support them. And so here's the agenda for the talk. I'll first start off with the scale of data infrastructure at Airbnb, along with the technology stack that we use. I'll cover our expansion from a single cluster to a tiered dual cluster setup with better reliability. With multiple clusters, one of the systems that we needed was data replication. And surprisingly, we didn't find a suitable solution that was open source. We decided to build one instead in-house with high throughput and low latency. Lastly, with all this data, you want a scalable way to manage it. So in the last part of my talk, I'll go over how we set up a data tagging system that enabled for easier management of your warehouse. So let's get started with the scale of data infrastructure at Airbnb. Airbnb aims to be a data-informed company, and it's one of the top goals for our year. We collect over 1 billion events a day, and we funnel all those events into our warehouse. Our warehouse is over 3 petabytes in size, and we have over 600 machines to support them. Just like our production infrastructure, our data infrastructure is all hosted on AWS. Overall, we're seeing data grow at a rate about 5x year over year. It turns out that this data growth rate is a little bit faster than the growth rate of traffic because it tends to scale with the number of engineers. More engineers mean more features, and more features mean more logging. And all that logging gets to our warehouse and really makes the warehouse pretty big. So let's talk about the technology stack of Airbnb. All those events, all those billion events, get funneled into our warehouse through Kafka, which is a PubSub system that we use. The tool for getting data from Kafka to HDFS is Kamui. It was made by LinkedIn. They have a new version out called Goblin. We're not migrating yet, but we'll probably do so eventually. And another big source of data for our warehouse are our MySQL databases. What we want to do on a daily basis is take a snapshot of those tables and get them onto HDFS. Our warehouse is based on Hadoop, and we have systems like Hive, Presto, and Spark that provide the computational framework. On our warehouse, we also have Mesos. It's a cluster scheduling system that enables us to schedule jobs pretty easily. Users sometimes interact with the systems in this layer, but more often, they interact with systems in the layer above. For example, AirPal is a web front end for Presto queries. And Airflow is a data authoring system for users to write and schedule Hive and Spark jobs. Since this talk is mostly about scaling the data warehouse, I'll focus on these two parts, Hadoop and Hive. For the rest of this talk, I'll assume that you guys have some familiarity with these two systems since they've been out for quite a while and they're pretty prominent in the data community. But if not, we can chat afterwards at the Q&A session. So our data infrastructure, like many others, started out as a single cluster installation with a single HDFS, MapReduce, and Hive. At the time, the most suitable instance to use was the C3 8X large instance with 32 cores, 60 gigs of RAM, and a little over half a terabyte of disk. This instance type was a little bit low on the storage side for a Hadoop application, so we actually ended up adding a 3 terabyte EBS volume to all these Hadoop nodes. Using EBS for Hadoop is a little bit questionable, but it actually turned out to work OK. Starting from a few clusters, we went from a handful of nodes. Starting with a few nodes, we went from a couple to over 800 by the end. One of the things that we tested was having data nodes on different availability zones. As you might recall, Hadoop keeps 3 copies of the data for data redundancy. The idea was that if we had a data node on each of the 3 different availability zones, we could get better fault tolerance. In case one AZ went down, we would have replica on the 2 AZs. It turns out, though, that this is probably not a good idea because network bandwidth and network performance between 2 AZs isn't that great. And so we actually don't recommend doing this. Our warehouse is entirely managed by Hive, which makes some of our warehouse operations a little bit easy. While pretty simple, we soon ran into scaling issues. And the scaling issues that we ran into was not really related to the software, but with the way that people use our cluster. With a single cluster, there's limited isolation between production and ad hoc jobs. Oftentimes, people ran an ad hoc job that used up too much memory, and that caused the task trackers to go out of memory. And this could affect other production jobs running on the same cluster. This made it a little bit difficult to meet SLAs, and it was hard to capacity plan as well. At the time, though, we were using Mesos to run the task trackers, so the damage was hopefully like a little bit contained with just the task tracker, but still having all those lost tasks wasn't great. Also, with a single cluster, it's actually difficult to roll out new versions of software. For example, let's say we want to try out a new version of the name node. Well, with only one cluster, it becomes like an all or nothing approach, where either upgrade or not. Also, with a single cluster, disaster recovery becomes a little bit difficult as well. Since you have only one cluster, if that one goes down, well, your data infrastructure is also kind of down as well. With all these challenges of the single cluster, we naturally moved to a setup with two different clusters. And our cluster evolved to a two-cluster setup with independent HDFS, MapReduce, and Hive metastores. By the time that we rolled out this new cluster, Amazon came out with some pretty nice instances. These are the D2 series of instances with a lot of local storage. For example, the D2 8X large instance, which is the instance that we decided to use, had over 24 terabytes of local storage. And this meant that we no longer had to use EBS. With the increased storage density, we could have much fewer nodes. And we only had about 250 nodes, down from 800 in the final setup. This saved a lot of money for us, and considering that data infrastructure is a pretty big part of our Amazon bill, it was pretty sweet. Now that we have two clusters, we set up replication of common and critical data sets between our production one and our ad hoc one. This is important because some of our data sets require a lot of CPU to generate. And if we had to run the same job on both clusters, it wouldn't be great in terms of utilization. Copying data is much more CPU efficient. For disaster recovery, we also put these two clusters on two different AZs. The idea is that if one AZ goes down, the other cluster was still available. And since we replicated common data sets, we could still continue to run critical production jobs on the functioning cluster. While the two-cluster setup has many benefits, it's important to keep some of the disadvantages in mind. Data synchronization isn't an easy problem to solve, and it's another system that you'll have to maintain and monitor. Also, with two clusters, data model isn't quite as simple, and it can cause confusion among users. For example, they might wonder, hey, why is this table out of date? Or maybe they were querying one cluster, and then when they switched to the other cluster, they forgot that they were in the other cluster, and asked why, hey, why is my table not there? Also, with two clusters, you've just doubled the operational overhead. You have more alerts, more systems to monitor, more metrics to track, and that sort of thing. And so to recap, here are the advantages and disadvantages of having multi-cluster setup. In general, having one cluster is pretty nice, and I think that's how everyone starts out. But once your DI becomes production critical, you'll probably want two clusters. But yeah, keep these advantages and disadvantages in mind. So now that we covered our infrastructure and the need for data replication between these two clusters, I'll go over the system that we built to handle data replication. The system that we built is both fast and has low latency. And this is because of its incremental nature. Since we're talking about distributed systems, one thing to keep in mind is that we'll be following the eventual consistency model. This means that if there are no new updates, data in both clusters will eventually be the same. It doesn't specify how long it will take, but in practice, the system will only be useful if this latency is pretty short, and hence the need for an incremental setup. With that said, for warehouse replication, there are two approaches. The other one is the batch one. In the batch process, we scan the entire HDFS or the warehouse, and then we copy the relevant entries. It's pretty simple because it has no state, but the downside is that the latency can be pretty high. If you have a very large number of entries to copy, and the fact that you're scanning the whole warehouse means that this job could take hours before your data is finally landed. The incremental solution starts by recording the changes in the source, and then only copying those relevant operations on the destination. It's a little bit more complicated, it has more state, but the advantage is that the latency can be pretty short, on the order of seconds. We favor this incremental approach because we actually wanted to make sure we could meet SLAs on the source, the ad hoc cluster. Oftentimes, pipelines that run on the ad hoc cluster couldn't run until those critical data sets arrive. And so having the data as soon as possible is a pretty important factor for us. And for this talk, since incremental replication is what we built, we'll focus on how we did it. So you can think of incremental replication being divided into 3 parts. First, you have to record the changes on the source. And then once you have those changes, you have to convert them into a set of replication primitives that you know how to run on the destination. Once you have those replication primitives, you actually have to go ahead and run them to make sure the clusters are in sync. So let's talk about the first part of recording the changes on the source. So as I mentioned in previous slides, all the data in our warehouse is managed by Hive. And this makes it a little bit easier to record those changes. Hive has a hooks API that can fire at different points in the query execution. You can have hooks that fire before a query runs, after a query runs, if a query fails, or even when any metadata changes in the Metastore. What we initially decided to do was to implement a post-execute hook that runs after the query has succeeded. This post-execute hook records the objects that the query read and wrote to. And by doing this, we can generate a log of all the changes that occur in the warehouse. This is like an audit trail. And even without replication, this is pretty useful because you have a list of changes that happen. And if you ever need to debug who updated this table last or when was this table changed, it's very, very easy to look through this log and see what happened. And so here's an example of what the audit log entry looks like. You can see it has some parameters like what the query type was and the actual query that the user ran. The parts that are most relevant to us are the inputs and outputs. These are the tables and partitions that the query read, along with the partitions and tables that the query wrote to. Since we're running Khronos on Mesos, we have a couple extra fields to record those job characteristics, but it's not really relevant for incremental replication. In addition to those entries before in the previous slide, we actually record even more detailed information. For the objects that have changed, we actually store the thrift serialized versions of those objects. This is much more detailed, and some of these details are important for incremental replication. And overall, with this kind of audit log, you can actually recreate exactly how the warehouse changed over time. OK, so now that we have recorded a list of changes on the source and then converted the list into a set of replication primitives, actually, we haven't done that yet, sorry. Once you have a list of changes, you have to convert those into a set of replication primitives. So in Hive, you can think of there being 3 different kinds of objects. There are databases, tables, and partitions. And with those 3 objects, there's only 3 different kinds of operations that you can really do: copy, rename, or drop. And so in essence, there will be 3 different kinds of replication primitives that you'll need to implement. A very important feature of these replication primitives is that when you create them, you'll want to make them to be idempotent. That is, running them once has the same effect as running them multiple times. I'll go over in a later slide as to why this is important. And here are a few examples of how Hive queries get converted into replication primitives. If you create a table on the source, that translates to a replication primitive to copy the table to destination. Same thing with creating a partition. You want to copy that partition to a destination as well. When you alter the metadata, that also translates into a copy operation. The copy operation copies both the data and metadata, so as long as that primitive runs, you're guaranteed that the source and the destination are in sync. Finally, if you rename a table, that also translates to a rename operation on this destination. So a lot of these replication primitives are kind of similar. There's 9 of them. So I'll go through a typical replication primitive and how it works step by step. In this case, this is the copy table primitive. Remember that for these primitives, you want to make sure that they are idempotent. The first thing you do is check if the source object exists. The reason why we do this is that we're tailing from the audit log, and it's possible that a user quickly created a table, then dropped it. And by the time we look for the table, it's already gone because it was dropped. If the source exists, the next thing you want to do is if the destination exists and is the same or not. Normally, won't be true, but if the partition, the table was copied beforehand, then it's possible that the table already exists and there's really nothing to do. If the table doesn't exist, you'll want to copy the data to a temporary location with DistCP. DistCP is a distributed copy tool that ships with Hadoop, but unfortunately, it doesn't make any guarantees that the copy is actually good. So once DistCP finishes, you'll want to make sure that the copy is actually correct. If the copy is good, then you finally move it to the correct location and add the appropriate metadata. The reason for copying a table in this way is that we can be efficiently idempotent, and we can also guarantee that the user never sees partial data. For example, because the metadata is added last, the user can't see the intermediate state where only part of the data was copied to the destination HDFS. In addition to the replication primitives mentioned in the previous slide, there's actually one more primitive that you need to implement to make this thing very efficient. And that is the copy partitions primitive. So remember that we use a DistCP job to copy each table and partition. And launching a DistCP job is actually kind of slow. It can take a second or two, and if you have thousands or tens of thousands of partitions, it can take a long time. So what the copy partitions primitive does is copies a bunch of those partitions in parallel. This is really to handle the dynamic partitioning case, where a user in a single query can create hundreds or even thousands of partitions. With this partition in place, with this replication primitive in place, you can copy a lot of partitions really quickly, and this helps to keep the overall lag for the system very low. So now that we've recorded the changes on the source, converted them to a set of replication primitives that we know how to run, you actually have to go about running them on the destination. And like with many things, there are multiple ways to do it. The first one is serial execution. It's pretty straightforward. If you have a list of changes and you apply them in the same order on the destination, you're sort of guaranteed to get the same result. Unfortunately, this is really slow. And for most production workloads, a serial execution workflow won't keep up with production demand. So the only other way to do it is to execute these primitives in parallel. Running them in parallel means it's fast and scalable, but this means that ordering becomes important. For example, if you're copying a table and its partitions, you'll have to create the table first before copying any of the partitions. And in the end, what you end up having is a set of DAGs that you need to execute on the destination. And so I'll sort of go over how this workflow goes in subsequent slides. Oh, and one more thing, when you're running these things in parallel, there are some data hazards to keep in mind when you have to recover from operations. And in order to make the system easy to run, there's some words I would like to say about failure handling. You want to make sure that this service can restart at any point with minimal progress loss. This makes it easy to deploy new versions of the software and also move this process to another service or another box when you need to. And this is really helped by the efficiently idempotent primitives that I mentioned in the previous slide. You can rerun these primitives, and it won't copy data that it already copied, so it will run very quickly. In addition, we checkpoint the Autolog ID periodically so that when the service does restart, it doesn't need to scan the entire Autolog of changes, and it can just resume from the last point that it saved. Recovering efficiently from a restart can be tricky in some cases. Consider this case where you create a table, drop it, and then create a table again. On the first pass, the replication process behaves as expected. It creates a table, copies it, drops it, then creates a new version of the table. But imagine the system had an issue and had to roll back and rerun some of these operations. It might drop the table unnecessarily and then recopy it. This is bad because it takes a long time to copy, and you might be wasting network bandwidth. Another case to consider is if you rename a table from A to B, and then you recreate the table A. On the first pass, yeah, it works as expected. But imagine the system had to roll back and redo the operations. In such a case, if the commands are run again, you might accidentally rename the wrong table. The table you copied over is like the new A. The simplest way to resolve these cases is to have some sort of versioning for these Hive objects to ensure that operations like drop and rename occur with the right table, or basically the problem is you have aliasing for the table names. where your table A can represent either an old version or a new version. And so with the version number, you can handle these cases pretty easily. And this is what our system does. So some facts about how our replication performance is going. Currently, it's replicating data from our production cluster. And in one of the tests that we did, which was an object count limited test with 60 threads, we got about 1.2 million objects copied and over 85 terabytes a day. The 85 terabytes a day figure is a little bit misleading because the test was designed to stress how fast we can copy small objects. With bigger objects, you can copy much faster, and in some sense, with big partitions or big tables, this figure can be like in the petabyte range. The system itself has second-level latency, which is great for meeting our SLAs. And after talking to a couple of companies, we found that this need was actually quite common. People start out with a single Hive cluster, and they move to multiple ones, and they need a system to keep these in sync. Because of that, we decided to open source the solution in early Q4 of 2015. And if anyone has an interest in running a pre-release version, feel free to contact James Mayfield or me for, I guess, an early version. James has been handling a lot of our open source efforts. And a lot of our open source projects typically have some sort of Air prefix to them, like Airflow, which was our workflow authoring system. So this system is probably going to be called like ReAir or something like that. But yeah, now that we went over the scale of data infrastructure at Airbnb, along with our cluster, our data replication system, in the last part, I'll go over how we do dataset tagging and management. Dataset tagging is pretty important because as your cluster scales, you'll want to tag certain datasets for certain warehouse operations. For example, you might want to back up these tables to S3, or maybe these tables contain private information, and so you want to scrub them. And so for these warehouse operations, it's very important to tag them so you can manage them very easily. Since our warehouse is in Hive, we decided to use the parameters field to have these attributes. The parameters field is an arbitrary key value map, and the advantage of using this is that it's very easy for end users to set. It's a built-in Hive command, so you can just run an alter table statement to add that tag to the table. The downside of setting it this way is it's easy to make a typo. For example, if you misspelled like backup or something, then that tag won't actually take any effect. And so you might want to write like a shell wrapper around it to make sure that only proper tags are set. Once the tags are set, you actually have to go about figuring out which tables and partitions in the warehouse have that attribute. And there's a couple ways to do it. Probably the most correct way in terms of API usage is to use the Thrift interface that Hive provides. Unfortunately, this can quickly become unscalable because this adds a lot of load to your Thrift servers. And also, as the warehouse grows, you'll have a lot of entries to process. The other way to do it is to process the metadata offline. If you had a dump of the metadata offline, you can use some other system to process it, and it won't actually add any load to production servers. And this method is pretty scalable. Lastly, probably the fastest approach is to process the metadata online and incrementally, kind of like how we did it for the incremental replication process, where we stream the audit log, look for changes, and based on those changes, we do some action. This is scalable and fast, but we decided to go with the middle approach of just processing the metadata offline. This is because for a lot of warehouse operations, like say backing up to S3 or cleaning up this PII information, it's not really necessary to do that as soon as possible. And so doing it sort of offline and in a batch format every day was a little bit simpler for us to manage. And so this is the solution that we went with. And since we're on AWS, I'll also sort of go over how we went about doing this. Our MySQL databases, much like the rest of our infrastructure, is also hosted by Amazon. And it's through their RDS relational database service. And one neat feature that they have is that you can create a separate point-in-time restored instance pretty easily. So what we do is that from our production instance of our Metastore, we ask Amazon to spin up another instance and replay it to a specific time. In this case, midnight UTC. Once this separate instance is up and running, we can use a scoop to copy metadata from this restored instance to HDFS. Once this data is loaded into HDFS, we can load it into a Hive table. And once it's in Hive, it becomes very easy and very quick to scan that metadata and look for tables and partitions that you want backed up. Another thing you can do is go through the HDFS stats through the FS image. This is another offline way of processing metadata. Basically, you can include stats like how big the table is and how many files there are by dumping the FS image to HDFS and running their OIV tool to sort of process that into a usable format. And one of the biggest cases that we have for this data tagging and discovery process is for backing up tables and partitions to S3. So what we do is that, we create a restored instance using the point-in-time recovery feature, generate a list of candidate tables and partitions, and we back up those to S3, and then calculate a checksum through a UDF as well. Once this backup process is finished, we set up the tags in the table. This is in the Hive metadata. And now we have a freshly backed up table or partition that is very easy to see because you can go into CLI and do describe formatted, and it will have those backup attributes. Some future work that we could do relates to incremental tag dataset discovery. This is like kind of using the incremental replication approach for detecting when these tags get set. It would get faster in terms of backing up stuff, and you also distribute the load throughout the day because instead of backing up at the end of the day, you can back it up as they get generated. But this is something that we'll probably look at a later time. So yeah, in this presentation, we went over the scale of data infrastructure at Airbnb, how we implemented data replication between clusters, and lastly, how we did dataset tagging and management. If you have any questions or thoughts, feel free to come by the office hours after the presentation, and I'll be happy to chat with you guys. And yeah, thanks for your time.